Hi, I'm Rob Kelly. I'm a professor in material science here at UVA and a member of the Center for Electrochemical Science and Engineering. My goals in this short video are to one, briefly describe the projects of mine that have openings for a graduate student, and two, describe a little bit of my philosophy of mentoring. So the first project on the left concerns the storage of spent nuclear fuel. Currently, there are about 3,000 stainless steel containers at nuclear power plants around the US contain many megatons of radioactive waste. These stainless steel containers are in these concrete casts you see in the upper left corner. They are waiting for the US to build and license a permanent repository for the waste, but that effort has been on hold for over a decade, so the power plants have to keep the waste locally. Now, these canisters are cooled by hot air rising out of the vents at the top of the cask and drawing cooler air from the surroundings through the bottom vent. But that cooling air brings with it a variety of corrosive species, which will deposit on the surface of the stainless steel. The concern is that these corrosive conditions will cause pits to develop on the surface, which will act as starting points for stress corrosion cracking. Penetration of the walls of the container would make later handling, whenever a permanent repository is ready, very challenging. So our work aims to help the Department of Energy classify which containers are most at risk. Sandia National Labs is already using a model we developed to predict the absolute largest pit size that can grow on a surface of these containers, given the surrounding environment and other information. The fact that that model does bound the pit size has been validated in laboratory experiments, but we don't know how conservative the prediction is. So if it predicts that a 200 micron pit could form, but in reality only a 2 micron pit can form, that's being overly conservative. So the student on this project will try to answer that question: how conservative is the maximum pit size model? And collaborate both with Professor Burns' group here at UVA, as well as scientists at Sandia. The second project there in the middle focuses on corrosion damage that occurs on critical structures in aircraft. It occurs because of contact of those aluminum structures with either a stainless steel or a titanium fastener. Currently, we are predicting the amount and location of the damage within the fastener holes. Those fastener holes are important because they're the areas of the highest stress, and they're impossible to inspect when the aircraft is assembled. So in our current work, we're considering the effects of water layer thickness, as well as the presence and action of corrosion inhibitors. The student on this project will extend that work to interactions that can be just as severe. Those are the accelerating effects of connecting carbon fiber reinforced composites, in addition to the stainless steel fasteners, to the aluminum structures. So the goal of that work is to provide guidance to the Air Force on what types of joints are most at risk and rules for repair designs as well as future designs of aircraft. The third project on the right involves the additive manufacturing of corrosion-resistant alloys. AM has immense promise as a means of manufacturing structures that are highly efficient and in many cases impossible to make any other way. However, many of the corrosion tests used on conventionally manufactured materials of the same composition give different results when applied to AM materials. In some cases, the AM material properties are better, and in other cases, it's worse. But it's not clear if these tests are actually reflecting the behavior that these alloys will exhibit in service. So this project will lead to improved specifications for corrosion testing based on a scientific understanding of the composition, structure, processing, performance tetrahedron that is material science. So the first two projects combine experimental modeling work, whereas the AM project focuses on experiments. And I'm happy to talk to you more about any of these projects, but I want to take a minute to explain what I see as my role as a mentor. My duty as a mentor is to help you develop from a student into a colleague. That is, someone who can work independently of me, attacking big, hairy, poorly defined problems and solving them. So no matter what you do after you earn your PhD, that set of skills will carry you a long way. Now, I approach that duty by making it my primary goal in working with you. The research project is the platform that I use to help you develop. But make no mistake, your development is the most important product we produce because it's the one that will have the impact on the world for the next 50 years. I love research. I love doing it right. I love doing work that has an impact on the world around us. but I'm in a university to help students grow, period. So thanks for taking the time to listen. If you have any questions about the project, my mentoring style, or anything else, send me an email at rgkelly@virginia.edu. Stay safe.